Hello, Pranay Koopa here presenting Chapter 5, Number 76. So basically the situation here is that there are people in a carnival ride, and basically it's a cylindrical ride, and they're in the inside of the cylinder, and the walls around it spin around, and the floor under the people disappear, and they spin at such a high pace, at a high rate that force friction keeps them up. And yeah, so that's basically the situation. So our known variables we have is the frequency. So we know that the ride revolves 0.5 revolutions per second. And we also have the radius, which is 5 meters. And right here, I wrote that velocity is equal to 2 pi rf, because we could convert this frequency into a angular speed just by multiplying it by 2 pi. And since linear speed is just angular speed times the radius, we get 2 pi rf. Alright, so now we go down to our force diagrams here. So first we have our vertical components. We have force friction static and force gravity. Force gravity is obviously down, but force friction static is parallel to the surface, so it's going straight up, and it's equal to force gravity since the people aren't accelerating up or down. And then we have force normal, which is radial towards the center of the circle, because since the people are moving in a circular motion. So first I write my sigma F statement, and I just get that force friction is equal to mg, which we can see that by the force diagram. And then I move on to my radial component rather, and then I write my Newton's second law, and we have this sigma F here, but there's only one force. We know that's force normal, so I say force normal is equal to ma, which is mv squared over r. And then right here, I plug this right here in for v squared, and a bunch of stuff gets canceled out, and in the end, we get our force normal as being 4 pi squared f squared mr. So the reason I found friction and force normal is because the problem is asking you to find the mu value of the ride to keep the passengers up and safe. So we need to know our friction force and our normal force for that. So then I write my equation for my static mu, which is just force friction over force normal, and I get mg over this thing over here. The masses cancel out, and then I get g over 4 pi squared frequency squared r, which when I plug in all my known values and my constants, I get 0.199 as my mu value. Alright, so there's also a second part to the question where the people say that they're described as being pushed towards the wall in the ride, and they're asking if there's an actual force. So if we in physics terms, we can just say that the people say that they're experiencing a force away from the center, and we don't see that anywhere in our force diagram, so there can't be any actual force. So the question asks us if there isn't any force, why do the people feel this way? And the answer is because of inertia, because a moving object will try to maintain its linear path, and will always try to move tangent to whatever curve they're moving in. So that's why they feel like they're getting pushed against the wall. Alright, so that's chapter 5, number 76. All done. It was pretty easy.